Hello and welcome back to our latest TechBites series. Today we have Hamamatsu's brightest young star Joe with us to discuss the topic of seeing beyond the visible. So Joe, to start, what is meant by this?
Thanks Victoria. As you may know, light can be thought of in a couple of different ways. In the particle approach, light propagates via force carriers called photons, whereas for the wave approach, we tend to refer to light as electromagnetic radiation. The electromagnetic spectrum describes all of the types of light one can perceive, ranging from radio waves at one extreme to gamma rays at the other. Towards the middle of this spectrum, you'll find visible light, a narrow band of colours that can be perceived by the human eye. At wavelengths beyond this, into the near-infrared, the human eye can no longer see this light. It is this near-infrared light, which falls just beyond the boundary of human vision, that will form the basis for this talk.
So what can this type of light be used for if we can't see it?
Good question, and the answer is quite a lot. I will describe some more specific applications later on, but one widely used general application area for near-infrared light is optical communications. Electromagnetic radiation, with a wavelength between roughly 1 and 2.5 microns, is generally defined as near-infrared light. Within this region, there are certain wavelengths, bands, which lend themselves towards optical communications. For example, 1550 nanometers is a commonly used wavelength for optical communications, as can be seen by this image. The absorption intensity of many regular gases is reduced in this region. This allows for less attenuation of signal when the light is transmitted through the air, known as free space optics. In addition to this, near-infrared light can help cosmologists learn more about the early universe. UV and visible light emitted by the first luminous objects have been redshifted to this infrared region due to the expanding nature of the universe. Therefore, by detecting this light, scientists can see back in time to gain information on the early formation of the universe. This is currently one of the major goals of NASA's James Webb Telescope, which you've probably seen in the news recently.
That's interesting, but how do we detect light in this near-infrared region?
InGaAs, or indium gallium arsenide, is a designer material with inherent sensitivity in the near-infrared. In its regular form, this compound semiconductor material can generally detect light with a wavelength falling between 1 and 1.7 microns. However, some applications require detection at longer wavelengths than this, up to 2.5 microns. In order to extend this wavelength range, the ratio of indium compared to gallium must be increased. However, this brings about its own challenges. To explain this, we must consider how the InGaAs material is produced in the first place. Standard InGaAs is normally grown on an indium phosphate substrate through techniques such as chemical vapor deposition or epitaxial growth. The InGaAs material and the indium phosphate substrate have very similar lattice constants, which enable isotopic growth. To put this another way, the geometry of the InGaAs structure matches up well with the substrate on which it's being grown, which is important to produce high quality material.
That seems like a lot of effort to go through to make this extended InGaAs. What's the importance of this material?
Extended InGaAs has many uses across a range of sectors and industries. For example, in biological imaging, the near-infrared light is better able to penetrate organic matter than visible light, allowing for deeper, non-invasive imaging. In addition, water has a strong absorption band in this extended InGaAs region, around 1.9 microns. Many applications make use of this absorption band to identify defects in products. Areas with a higher concentration of water appear darker due to more of this light being absorbed. This can be applied to a number of areas, such as food quality inspection, to test for bruised fruit and vegetables caused by a build-up of water. In pharmaceuticals, it's also important to test for water content. As you can see from the two images on screen, imaged with visible light, these two tablets look identical. However, under near-infrared radiation, we can see that one image is significantly darker, inferring a higher water content. In pharmaceuticals, this is important as the water content can affect how the API, or active pharmaceutical ingredient, reacts with the body. In this case, the water content can also affect the shelf life of the product. Therefore, the ability to image at these wavelengths with extended InGaAs can be invaluable for various inspection processes.
That's quite a range of applications. Are there any more uses for this technology that we should know about?
For sure. As a sales engineer in our industrial group here at Hamamatsu, one common application I encounter is the monitoring of laser beams. Generally, customers are interested in determining the profile and size of the laser beam. If these laser beams extend beyond 1.7 microns, extended InGaAs can be used for these measurements. To demonstrate this principle, I will use one of our extended InGaAs detectors. At Hamamatsu, we can offer InGaAs detectors in a variety of package types, ranging from TOCAN to thermoelectrically cooled components. Here, I have one of our new InGaAs image sensor modules. This can be thought of as a starter kit for evaluation, with the module taking the format of a camera. This module contains all of the readout electronics required and can be offered with a C-mount adapter and USB connectivity to a PC. This module, part of our C16090 series, contains a temperature controller. This is of particular importance to an extended InGaAs module. As the operation temperature decreases, the inherent band gap of the InGaAs material widens. This causes the number of carriers thermally excited from the valence band to the conduction band to decrease exponentially. The unwanted movement of charge carriers crossing the band gap is defined as the dark current, which is a source of noise in the system. Therefore, having a temperature controller to operate this module at -20 degrees enables a higher signal-to-noise ratio, leading to improved results. For this demo, I'm using an Energetic laser-driven light source. Energetic is a Hamamatsu-owned company, and further details of this light source can be found in my colleague Kirsty's TechBite video, so be sure to check that out after this. A key feature of this image sensor module is the background subtraction tool. To show how this works, we first must capture a dark image with the lens cap on. This image can be saved into a folder of your choice here. To enable background subtraction, we then need to perform image processing. As you can see, the dark image now contains much less thermal noise. This is even more evident when we open the lens cap to image the light beam. With the background subtraction on, there is a very clear distinction between the signal and the surrounding dark areas. However, turning this background subtraction back off reintroduces much of this noise into the image, and it is much more difficult to distinguish the signal from the surrounding noise. Even after the background subtraction, however, there can still be some noise patterns on the output image. These can be caused by the back thinning procedure of the pixels that make up the image sensor. To correct for these, another feature of this module, known as shading correction, can be used. If you're interested in learning more about the features of our InGaAs image sensor modules, please get in touch with us. We can organise demonstrations of a range of our InGaAs modules and cameras, including this model, to help you determine the suitability of the device for your particular project. Please email us or give us a call and we'd be happy to discuss your project in further detail.